Hello, and welcome to Minitab Statistics for Second Language Research. This is Lesson 9. In this lesson, we're going to learn how to perform a chi-square test. Two kinds of chi-square tests. This is based on a supplement on Larson Hall's webpage for the book A Guide to Doing Statistics in Second Language Research using SPSS and R, and we are translating it into Minitab. Before we talk about chi-square, let's see where chi-square fits in the big picture of hypothesis testing. At the beginning, we said that there are two kinds of statistics, what we call descriptive statistics and inferential statistics. We're going to review a little bit about those two types. Then we're going to discuss the factors that we have in order to choose a correct statistical method for our data. And finally, we're going to talk about parametric and non-parametric procedures. And chi-square will be a non-parametric procedure, as we will see. When we talk about descriptive statistics, we use statistics to describe the sample and summarize the information about the sample. When we do inferential statistics, we use statistics to make inferences or generalizations about the broader population. So from our data, we expand the results to the whole population. We have three factors to consider when we do statistics. First, the research design, then the levels of measurement and types of variables, and finally we have to talk about the assumptions that we need to have. Regarding the research design, notice that we have what we call correlational research. And in this case, we're going to examine the extent to which two or more variables relate to one another. So in this case, that would be a correlational hypothesis. If we are interested in finding out the formula for that correlation and make predictions, then in that case we have what we might call a predictive correlation. Now for the pure correlation, that's what we call correlation. When we are trying to do the prediction, that's when we would use regression. And those were the topics of our first inference statistics lessons in this program. Once we have the basic data, then we want to get experimental. And then we have three levels here. We have what we call the pre-experimental, the quasi-experimental, and the true experimental. For the pre-experimental, we need to get data, and the data are going to tell us whether we are in for a deeper treatment. With the quasi-experimental design, we are going to determine whether there is a cause and effect in the treatment. And then finally, when we have the true experimental design, this is when we carry the full experiment to see whether that relation or correlation that we saw at the beginning is true or not. So here we have the big picture for quantitative research. Now, also regarding the research design, we can do three kinds of experiments, what we might call between group experiments. Now in that case, when we're comparing between groups, we are going to use the independent t-test and the between group ANOVA. We can also do within group experiments, and in that case we would use the dependent t-test and the within group ANOVA. And finally, we can just have non-experiments where we just look at the correlation, and in that case we just use Pearson's R. When it comes to the levels of measurements, we have qualitative and quantitative variables. Now the qualitative or categorical variables, notice that to report these, we're going to use frequency tables, bar charts, number and percent of cases in each group, or the mode. The mode is simply the highest value that we get in our data, the number that is going to be repeated the most. That is what we call the mode. Not very much used in language acquisition. As for the quantitative variables, we can also have frequency tables, but we can use histograms. We will use the mean and the median, and of course the variance, the standard deviation. We're going to be using that a lot, and the minimum, maximum, and the range that we discussed in previous lessons. When it comes to tests, there are going to be two kinds of tests, what we call parametric and non-parametric tests. Now, parametric tests, they make a number of assumptions about the population from which the sample has been drawn. So in that case, we need to make sure that we have normally distributed scores, so normal distribution, and also we need to have what we call ratio or interval data. Remember, ratio is also called continuous data or interval data. For non-parametric tests, the techniques do not have such stringent assumptions. So for example, we don't need to be normally distributed, or sometimes when we have smaller samples, then non-parametric tests are going to be advised. And also notice that we would use non-parametric tests when we have ordinal or nominal data. The problem with non-parametric tests is that they are not as strong as parametric tests. So ideally, in language acquisition research, we have to use parametric tests when we can. Finally, when it comes to the assumptions, normally there are these three assumptions that we need to make sure we have before we start our testing. The first one is normality. Then we have to make sure we don't have extreme outliers, and then homogeneity of variance. This is what we called homoscedasticity before. Now here then you have the types of data, and then the types of variables that you're going to get, and then finally the analysis that we recommend. Now, for the types of data, remember that we had nominal, ordinal, interval, and ratio type of data. And the interval and the ratio data, those are the ones that are going to allow parametric tests. We will talk about parametric tests in a second. So these are quantitative sort of data. Notice that ordinal data is also considered quantitative data. However, it does not allow for parametric tests. So nominal and ordinal data, they're going to allow only non-parametric tests. In this chart, you have here the parametric and non-parametric tests. As you can see, most of the parametric tests that we have studied have a corresponding non-parametric test. So for example, for the independent sample t-test, the equivalent non-parametric version would be the Mann-Whitney U-test. The paired sample t-test, you have the Wilcox-Sum and the sign-rank test. One-way between groups ANOVA, that would be the Kruskal-Wallis test. The one-way repeated measures ANOVA, that would be the Friedman test. Now for the two-way analysis of variance, we don't have an equivalent non-parametric tests. Now we have concentrated on the parametric tests. If you're interested, we can have another session or another course where we study about non-parametric techniques. But as I said, usually in language research, you're going to find parametric tests all the time. The exception, however, is going to be the chi-square. So chi-square, notice that these are also going to be non-parametric tests. However, we do use them, and you will find them in some studies in language acquisition. And we have two types here. We have what we call the chi-square for goodness of fit, and we have the chi-square for independence. And this is the topic of our lesson today. Now, how do we calculate chi-square? The formula you have there, okay? So normally we represent that with a chi, or in Greek it's called chi, square. And the formula then is you're going to sum all the observed frequencies and you're going to subtract the expected frequencies, and once you subtract this, you're going to square that, and you're going to divide that by the expected frequency. So this is the formula that we have for chi-square, and I will demonstrate in a second how this works. So imagine here, for example, that I have a die. Okay, now a die has 6 different values, right? You can get a 1, a 2, a 3, a 4, a 5, and a 6. Now imagine that I throw my die 100 times for each number. So I'm going to throw my die for 600 times. Okay, so I throw my die 600 times. Now, if this is a perfect world, then I would expect to get 100 times each number. So for the 600, I would get 6 times 100. So every number would get 100 times. Now, this is never going to happen, you see, but this would be the ideal. Now, let's imagine a situation where we throw the die 600 times and we get the values there under O. Okay, so O is what we call the observed data, and then E is what we call the expected data. So we expect 100, but notice we never got 100. We always got around 100. So we got all the way from 124 to 81. So the question that we're going to be asking then is whether this is a normal situation. This is within the expected range of variation that we should get. Now, to calculate chi-square, the first thing that we do then is we take the observed value and we subtract the expected value, and that's what you have in the column here. Okay, so we take the observed value and we subtract the expected value. Now, once we get that value, we square that value. Okay, so there we have the square values for the previous column, and then once we get the square, then we divide that by the expected value. Okay, so we get all these numbers here on the last column on the right. Now, if we add all those values, then that is what we call chi-square. So in this particular case, notice we would get a value for chi-square of 12.26. Okay, 12.26. That's going to be the chi-square for the data that we got under O. Now, the question is this then within the acceptable variation that we have for the die, for the throws of the die? So in that case, notice that we need to go to a chi-square distribution plot, and here then we have calculated the critical value for our data. The critical value is 11.07. Now notice that we got 12.26 in our data, and as you can see, the 12.26 here is going to be in the reject area. So in this case, we're going to say that this is not within the normal range of throwing the die. So this die somehow is loaded. Okay, so someone is cheating because we're not getting the correct distribution that we should be getting. This is all, of course, within the 95% confidence level that we have here. Now, once we run a chi-square, we're going to get a chart like this. Okay, so notice that we get here what we expect. So we expect to get 100 all the way for each one. This would be the perfect world, but this is what we actually got. Okay, now the proportion that we would get would be, we would expect to get about 16.66% for each one, but notice that actually what we got is basically this here. Okay, so the program Minitab is going to submit all the data here to the chi-square test, and we are going to test this hypothesis. This is going to be then the null hypothesis. There is no significant difference among the values, so that means every value has the same chance of occurring. Now here we will get the report for the data, and the report will say that we threw, you see, n 600 times. We got 5 degrees of freedom. The chi-square that we got was 1226, as we saw before, and it gives us a p-value. Now that p-value is 0.031. Notice that this is low compare to 0.05, which we usually compare with. So P is low, H null must go. So in that case, we reject the null hypothesis, and in this case then we conclude that our data are not distributed similarly. Okay, so there is a significant difference among the values. We reject the null hypothesis. Here we will get a chart, and as you can see, the brown bars is what we would expect. We would expect, you know, exactly the same number of throws for, you know, each number, but the blue lines represent what we actually got. And, you know, for the simple eye, we cannot conclude that this is a true, let's say, value or not. So that's why we need to run the chi-square test. Normally, when we report these type of data, notice that now we are dealing with non-parametric tests. We can report them in what we call a pie chart. So here's a pie chart, and as you can see, it's a pie, and each little section here, each little color, represents then a number. So this is number 1, number 2, number 3, number 4, number 5, number 6. And then this then is going to tell me also the percentages. So in this case I have 18%, 0.5 for number 1, and so on. Okay, so this is one way to represent the data. You can do the chart, or you can do this particular graph. Another way is to do it with what we call a bar chart, and we will learn how to do this in Minitab. So here you have then the numbers, so 1, 2, 3, 4, 5, 6, and the number of times that we got that number. So for number 1 we got it 111 times, 90 times for number 2, 81 times for number 3, and so on. So a bar chart. Okay, so let's go to Minitab, and let's open the file called chi-square goodness of fit, and we're going to do the problem that Larson Hall has in her chapter. This is a language department. They teach 5 languages: Chinese, Spanish, French, German, and Japanese. And there we have the number of students that have signed up for each language. As you can see, the number varies from 13 in German to 29 in Japanese. Now, the question we're going to be asking is whether the students are distributed evenly in the school. And of course, it looks like they are not, right? It looks like Japanese took a large brunt of the students, while German did not. So we're going to do a goodness of fit, because in this case, we only have one variable. So if we have one variable, we need to do a chi-square goodness of fit. So let's go to stat, and then the chi-squares are going to be under tables. So stat, tables, and notice that here we have chi-square test for association. This is when we have more than one variable, and here we have chi-square goodness of fit, one variable. Okay, so we click here, one variable. Now, when you click here, notice that it's asking you for counts. Now, we don't have a variable with counts, because here all we have is just the number for all the languages. And then it's asking us for categories. These are all the categories. So notice what happens here then is that we have the data in the wrong way. Okay, so here we've presented the data horizontally. What we need to do is present the data vertically. So what I've done here in worksheet number 2, you have the data, the same data, vertically. Notice Spanish 20, French 15. Okay, so here we had Spanish 20, French 15. So we have exactly the same data, but now we have the data vertically. Okay, so you have to have the data in the right order, in the right way, so that Minitab can analyze that. So now let's go back to stat, let's go back to tables, stat tables, and now we're going to try to run the chi-square goodness of fit for one variable. Notice that we only have one variable, and in this case the variable is just languages. So we click OK. Now notice that it's asking us for count and category. Now it's easy. Count is count, okay, because we have the number of students that we have for each case. And then the So count is going to be under count. So let's put it there. And then categories, this is going to be our languages. Okay, so languages is going to be our category, and count is going to be our count, the number that we have for each case. The graph is automatically going to give us a couple of charts. We will see that in a second. So let's just click OK. So we click OK here. Notice that here, as we can see, we had 100 students. Okay, if we have 5 languages, then we would expect 20 students in each class. If they are evenly distributed, we would expect 20 students in each class. What we observed is here. Notice that, as we said before, we had all the way from 13 students in German to 29 students in Japanese. So that's what we observed. Now, the proportion then, we would expect 20% in each class, okay? But this is what we actually got, okay? So this is the distribution to chi-square. Now, notice here then that we have the number of students is 100. The degrees of freedom is 4. How was the degrees of freedom determined? To determine the number of degrees of freedom, here notice that we have 4 degrees of freedom. What we do is we look at our categorical variable, and in this case we had 5 elements in our categorical variable. So we take that number and we subtract 1. So 5 minus 1 is 4. That gives us then 4 degrees of freedom for this particular test. Notice that here we got a chi-square of 8.2 with a p-value of 0.085. So p is higher than 0.05. P is high, the null can fly. So in this case, the null hypothesis is that the languages are going to be evenly distributed. Now in this case, P is high, the null can fly. Yes, the languages then are evenly distributed. Now when we look at the chart, notice that the yellow is what we expect, and the blue is what we actually observed. Now, to the simple eye, they look like they're not evenly distributed, but notice that the chi-square actually told us that, yes, statistically, they would be considered to be evenly distributed. To confirm this, we can run the assistant. So go to Assistant, Hypothesis Test, and here on the very left side, you have chi-square goodness of fit. So click on that. If you click on that, then let's call this Hometown University. And then notice that you have your languages here. Now, simple count, go here and you're going to go Hometown University. And the target that we want is 20% for each one, so to see whether they're evenly distributed. So here, put the name of the university. Here you're going to get the outcome. So these are the languages and the count. Make sure here then that you put Hometown University. That's the one that we are checking. And then we expect 20% in each one. So click OK. If you click OK, notice that this is going to be confirmed here. It says the percents for Hometown University are not significantly different from the target percent. Notice here it gives us a little chart saying that yes, we were expecting 20 for each one of them. We got these numbers here, and we're saying that they do not differ. Here we have the same chart that we got before, but now we have it horizontally, and you can see then that the sample is the blue one, and the target, the 20%, is the lighter blue. Now, they don't look like they're the same, but statistically, the program has determined that they are actually distributed evenly. Now, let's learn how to make a pie chart. So for that, we're going to go to Graph, and then you go down all the way to Pie Chart. So Graph, Pie Chart, click OK. Now notice that it's asking you for chart counts of unique values. We don't have that. We have chart values from a table. Now in this case, we have the categorical value. So the categorical variable that we have is languages. and where we have the count, it's the count. Okay, so the summary variables is going to give us the number. So we go to chart values from a table, categorical values, we enter our categorical variable, and then we enter the count that we had for that. We click OK. So notice that we get our chart here, okay? And notice that the slices are different in sizes, okay? So some are big, some are small, so we can see here the Japanese is the one that is going to be the largest, and then the German is the one that is going to be the smallest. So this is a good little window to have here that tells us which language. But we can add more information to our chart. So we go to double click anywhere on the chart and then go to add, and we're going to add slice labels. So add slice labels, and it's asking you what do you want to add to the chart. So notice that we can ask the name, and we can also add either the frequency or the percent. So maybe we should add both. And then draw a line from label to slice, no, okay? So click OK. So notice that now then we got all the information for each language. So now we have the language here, and we have what percentage that accounted for. And also that the first number that you get here, that is going to be the real number. So you can either enter both or you can enter just one. So here it's okay to have both. Okay, and you can have that inside. So imagine, for example, that you want to have this inside the chart. So you just click on this and you move it here, and then it will be inside the chart. You can have it inside or outside, doesn't matter. Let's leave everything inside. Okay, so we can put everything inside. Now once we put everything inside, notice that this little window here is going to become useless because we already have the name of the language with all the information here. So we want to get rid of this, so click on that, and then just, you see, once you get the little window there, click delete, and then the window goes away. And here you have then the chart with all the information, and click OK. Now if you want, then you can transfer this to your document. So as usual, click on the arrow, send to Word or send to the PowerPoint, and you got the little pie chart. You can also do bar chart. So you can go to graph and then go down all the way to bar chart. So graph, bar chart. And once you're in bar chart, you are going to go down to values from a table. Values from a table. And we're going to go simple graph. Click. Then notice that it's going to ask you for graph variables and categorical variable. Now for the graph variable, notice that you only get the choice of count. So you enter count, and then for the categorical value you would enter languages. That's the categorical variable that we are trying to graph. Click OK, and there we have our chart. Okay, so now here we have the languages with the corresponding count of students that we have there. Now, sometimes, like in this chart, for example, it is hard to actually read the number. So here we can see that it's 20, but this one I'm not sure if it's 16 or 17, so we might want to add that information. So again, click anywhere on the graph, go to Add, and then we're going to add data labels, okay? And we want to use the Y values, so click OK, and then notice that automatically that added the count that we had for each language. So for Spanish we had 20, French we had 15, and so on. So click OK, and again, if you click on the arrow, you can send that to Word or you can send that to PowerPoint. So now you learn how to do then a pie chart for your data, and then you also learned how to do a bar chart, and you also learned then how to perform a chi-square goodness of fit test. Now remember that you do chi-square goodness of fit when you have only one variable. And in this case, we only had the variable of languages. Now we are ready to discuss the chi-square test of independence. In the introduction, we mentioned that we have two types of chi-square tests. we had the chi-square goodness of fit. Now in that case, we had one university with 5 different languages, and we were trying to determine whether the languages were evenly distributed. Now in the chi-square test of independence, we are going to have the same 5 languages, and we're going to have 2 universities now, Hometown University and Big City University, and we're going to try to determine whether the 2 variables are actually independent or not. That's why this is called the chi-square test of independence. In the first case, we had one categorical variable, which was language. In the second case, in the chi-square test of independence, we have 2 categorical variables, language and university. As you can see, we have the same 5 languages, but we added the university variable, and now we have 2 university variables. Now, in this case, notice that in the first case, the chi-square goodness of fit, we have 1 row and 5 columns. So basically, the rows tell us how many categorical variables we have. In the second case, we have 2 rows and 5 columns. Again, the 2 rows tell us that we are dealing here with 2 categorical variables, 2 rows and 5 columns. Now, what is the formula to determine the chi-square test of independence? You have it there. So the chi-square test of independence, we will take all the observed values, and then we will subtract the expected values, we will square that, and then we will divide that by the expected values. Now we will do this both for the columns and the rows. This is why here you have 2 sigmas. So the first sigma here, we do that for the columns, then we do that for the rows. The same operation for the columns and the rows. Now to determine the denominator in this case, we take the row, the number of elements that we got for the rows, and then multiply that by the number we got for the columns, and we divide that by the grand total, and that gives us then the chi-square test of independence. Now in this case, the null hypothesis basically will say that the variable 1 is independent of variable 2. This is the null hypothesis. Then the alternative hypothesis is that variable 1 is not independent of variable 2. So this is why this is called the test of independence. Another way of formulating this is to say that variable 1 is not associated with variable 2, or the alternative hypothesis, variable 1 is associated with variable 2. So there's 2 ways to formulate the null hypothesis in this case. Now the requirements to run the chi-square test of independence, basically we need to have 2 categorical variables, only 2 categorical variables, 2 or more categories for each variable, so we can have more subdivisions for those categorical variables. We must have independence of observation, so that means that there's no relationship between the subjects in each group, and the categorical variables are not paired in any way, so we are not dealing here with pre-test or post-test derivations and observations. And then we need to have relatively large sample sizes. Okay, so the expected frequencies for each cell, we need to have at least 1, and the expected frequencies should be at least 5 for the majority of the cells. Okay, so we need to have 5 values for each of the cells that we are trying to compare here. So now let's go to Minitab and see how to run chi-square test of independence, also called test of association. Now here, remember that we had worksheet 1. This is where we had the languages and then the number of students that signed up for each languages at one university. We saw that we had to rewrite the data this way. So we had to have 2 columns, and then one column would be the column for languages, and then the other column would be the count for those languages. That's the only way that we could run the chi-square goodness of fit test. For this one, let's see if we can run it this way. Okay, so here we have the languages as columns, and we have the universities as rows. Okay, let's see if we can run our test of independence that way. Now in Minitab, the test of independence is called the test of association. So we go to Stat, Tables, and as you can see, this is going to be the chi-square test for association. So Stat, Tables, chi-square test for associations. Now, here we are going to have then summarized in a two-way table. Now here it says columns containing the table. So summarize data in a two-way table. So we have the columns. Our columns are going to be the 5 languages. So we enter the 5 languages in our columns. And then it's asking us, it says optional here. Now in our case, the rows are the university. So we're going to put here university, and the columns are actually the languages. Okay, so university and languages. Okay, so rows, university, columns, languages. This is the way we have organized our data. So we click OK, and we see that we get here a very nice chart with the names of the universities and the languages. Okay, now here the first number here, the top number, is going to be the count, the observed count. And then the second number here is the expected count if the two variables were to be related. Now the important value here, however, is going to be the chi-square test value. Okay, so in this case we get 8.374 with a p-value of 0.079. 0.079 is higher than 0.05. P is high, then null can fly. So that means then that the two variables here, the university and the language variable, are going to be independent of each other. They're independent of each other. So that means there's no relation between what happens at one university and what happens at the other university. If we set up the data in a different way, this way, where we have all our variables as columns, then let's run the test and see what happens. Okay, so Stat, Tables, we're going to do the chi-square test for association. Now in this case, the columns are going to be our universities. Now the rows in this case are the languages, and the columns in this case are the universities. University. Okay, so let's click OK, and here we have then columns of university. So here it basically gives us the same chart but in a different direction. Now what we have here are the languages, and then the scores that we get, the numbers that we get for the two universities. I think the previous chart looks a little bit better for your report, but you can pick whichever chart you prefer. Now the important thing here is going to be the chi-square. So notice that here we are getting a chi-square of 8.374 with a p-value of 0.079, just as we did before, and in this case P is higher than 0.05, P is high, null can fly, so that shows again that the two variables, university and languages, are independent of each other. Now, since they're independent of each other, then there's another test that we can run, and we can see whether the languages are evenly distributed at the second university. So we can run a goodness of fit for that case. So let's go Tables, chi-square goodness of fit, and here then we have observed counts. So in this case we have hometown university. We did that before, so we are going to, there we go, we are going to run it for big city university, and the category names in this case are going to be languages, and let's run OK. So notice that it ran the test and it gives us a p-value of 0.02. A p-value of 0.02 is lower than 0.05, so p is low, the null must go. So in this case, it means that the languages at this university, the big city university, are not evenly distributed, unlike what we observed at my hometown university. We can reconfirm this if we go to the assistant, hypothesis tests, and then chi-square goodness of fit. So here, let's call this big city university. And what we have here then, we have the languages. And now we're going to run this for big city university. And of course we are expecting the same, so that would be 20 in each one. Run it. If you run it, then notice that it says the percents for big city university are significantly different from the target percents. Okay, so now we do get a significant difference in the distribution of languages at big city university. As you can see here, they look different. Now remember that before they did look different also, but again you have to let the test decide whether they're significantly different or not. Here in the chart you can see that we're expecting 20 in each one of them, but in one of them we got all the way to 26, and the lowest we got was 24. So here chi-square has determined that these are significantly different. We can now use the assistant to also run the chi-square test for association. So go to the assistant, chi-square test for association, and here what you need to do is you're going to get from the current worksheet, and we have them in rows. Okay, now here for the outcomes we're going to do the languages, and we have 5 outcomes, so we have 5 languages. Here you're going to put one university, so let's put hometown here, and automatically it enters the values. And then here we're going to put big city, and automatically enters the values. Okay, so make sure you do your worksheet in the right order. Okay, so here you have to get from current worksheet, and then number of outcomes. You have 5. We have 5 languages, and then here you're going to put one university, and the other university, of course, 95% confidence interval, and we click OK. Here's our report card, and we got a p-value of 0.079, which is higher than 0.05. In this case, our null hypothesis was that the languages would be distributed the same way in the 2 universities. Now, p is high, the null can fly, so that means that yes, languages are distributed the same way in the 2 universities, even though to the eye it doesn't look so. Here you can see the distribution of the different languages. This is the average, and this is what you get at hometown university. This is what you get at big city university. Here we get the observations and when we would expect if they were the same. And then our final report card says that all samples are large enough to obtain sufficient expected counts, so the p-value for the test should be accurate. So we conclude then that even though to the eye it looks like languages are distributed differently at the 2 universities, statistically there is no difference in the way the languages are distributed at the 2 universities. Okay, so now it's time to discuss how to write the report when we do a chi-square test. So we're going to start with the one-way goodness of fit chi-square. Now here is the little summary of what we got when we were analyzing hometown university. So we had a little summary of the observed values as opposed to the expected values, and the result of the chi-square test. Okay, so the important thing here to remember is going to be the degrees of freedom, the number of course, and the p-value. So this is the way we would write it up. The one-way goodness of fit chi-square test was conducted to determine whether there was a statistical difference in the distribution of the number of students in the 5 language classes offered at hometown university. The corresponding contingency table is shown below. So 2 important things here. One is that we need to say what kind of chi-square test we performed. Remember that there are two kinds of chi-square tests. So in this case, we are running the one-way goodness of fit chi-square test. The second point is that it's very important to include the contingency table, because that summarizes, and you don't need to summarize one by one, all the different cases that you have. So you can see the observed cases and the expected cases and the contribution to chi-square. So the contingency table pretty much does the job that you want here. Then we continue. The test yielded a chi-square value of 8.2 with a corresponding p-value of 0.085, thus showing that there is no significant difference in the distribution of students among the 5 languages at Hometown University. So then notice that you must report the chi-square value, the p-value of course, and then your conclusion. So in this case we have chi-square value of 8.2, a p-value of 0.085, and the conclusion then is that there is no significant difference in the distribution of students among the 5 languages at this university. Okay, so this is the way we would write up the goodness of fit chi-square test. Now let's look at the way we will write up the two-way group independence chi-square. So here again is our little summary. So we have the 2 universities and then the results for each of the languages here. Then we have 2 scores reported here. We have a Pearson score and a likelihood ratio score. Okay. However, we are missing the effect size. We need to report the effect size, and in this case the way we report the effect size, this is called Kramer's V square. Kramer's V square. Now unfortunately Minitab does not provide us with Kramer's V square, so we will have to do this online. Okay, so to do this we're going to go to vasarstats.net/newcs_HTML ? Okay, so this is the address that we have to go to, and I'm going to go there and I'm going to show you how to do this. So this is what the web page looks like. As you can see, it says chi-square, Kramer's V, and lambda. We'll talk about those later. Here you will select the number of rows and columns. I will show you how to do that. Here you will enter your data, and then here is going to give you the result for chi-square, degrees of freedom, the p-value, and Kramer's V. This is actually what we want. So I'm going to go back now to the PowerPoint, and I'm going to show you what you're going to be doing and entering here. Okay, so this is the web page, and then make sure then that we are www.vasarstats.net/newcs.html ? Now here, that's the address. What interests us here is basically this chi-square and Kramer's V. That is what we are after. Now Kramer's V is a measure of the strength of association among the levels of the row and column variables. Okay, so this is equivalent to what we were doing before with our R square. Okay, this is going to determine the strength of the association. Here we have to be careful then. We need to select the number of rows and the number of columns that we have. So in this particular example, notice that we have 2 universities and 5 languages, so we're going to choose 2 rows and 5 columns. Once we choose the rows and the columns, we enter the data. So this is pretty much the same data that we had in Minitab, and you enter the data. So here the B's are the ones that correspond to the languages, and the A's are the ones that correspond to the universities. Then after that you press on calculate, and this is going to give you then the results. And as you can see here, you're going to get a chi-square, degrees of freedoms, and P. Now this is not any different from what we actually got when we were doing Minitab. Notice that the chi-square corresponds to what Minitab calls Pearson's chi-square. The degrees of freedom are the same, and the p-value, Minitab has approximated 1 decimal, so here you have 0.0789. Okay. However, in your report, you're not going to be reporting Pearson's chi-square. Rather, you're going to be reporting the likelihood ratio and the p-value for that. Okay, so this is why we still need to do Minitab. Now, what is important to us, however, is that here we get the value for Kramer's V. Okay, remember this is going to measure the strength of the association, and this is similar to what we were doing before with the R value that we were doing before, that it went from 0 to 1 or -1. So in this case, 0.2, that's a very weak association. The other thing that is important here that you will get on this web page is the confidence interval. Okay, so notice that here you're going to be getting the 0.95 confidence interval, and that needs to be reported. So it goes from 0 to 0.4045. Okay, so that's the information that you need to get from this web page. Now, how do we write this up? Well, first, the same as we did before, let me read this and then I will explain what we're doing here. So it says, a two-way group independent chi-squared test was performed to assess the distribution of the number of students in the two universities. The corresponding contingency table is shown below. So two things are important here. You say what kind of chi-square test you performed, and then show the contingency table, because that summarizes everything that they need to know. You don't need to summarize that in your description. The contingency table has that information. Now, this is the information that we got from the web page. The effect size of Kramer's V square was 0.2046 with a 95% confidence interval of 0.1145, 0.4045. Okay, so here you report the confidence interval. The formal statistical results of the test were the following: likelihood ratio chi-square, so that comes from Minitab 8.489, degrees of freedom 4, p equal to 0.075. This result shows that there is no statistical difference in the distribution of students in the different languages between the two universities. So what do we observe in this description? Well, first, we report Kramer's V square, we report the confidence interval, you report the likelihood ratio chi-square that comes from Minitab with the degrees of freedom and the corresponding p-value, and then your conclusion. So in this case, there is no statistical difference in the distribution of students in the different languages between the two universities. Okay? All right, so now time has come to talk about your last assignment. So for this, we're going to use the data in the Wall and Pavlenko 2003. This comes from a web questionnaire where they were measuring bilingualism and emotions. These are people from the University of London. And the respondents at least had 2 languages, minimum. Okay, so this is all for people that have more than 1 language. And they had 2 categorical variables. One was the L1 dominance, and the other one was the degree. So they were trying to establish whether there was some sort of relationship between the dominant language and the degrees that you have in life. So for the dominance, they're using 3 categories here. Yes means you're L1 dominant. No means that you're dominant in another language beside your L1. And yes plus means that you're dominant in more than 1 language. Okay, so these are the measures for L1 dominance. Okay, so yes means L1 dominant, no another language, not L1, and yes plus means you're dominant in more than 1 language. Now the degrees, these are educational degrees. So 1 corresponds to high school, 2 corresponds to BA, 3 corresponds to MA, and 4 corresponds to PhD. Okay, so this is pretty much the way that the data are going to be presented. Now, here's your last task. So you are going to ask the questions. I'm not going to ask the questions. So you will ask 2 research questions based on the data. One question must require you to perform a one-way goodness of fit chi-square test, and the other question must require you to perform a two-way independence group chi-square, respectively. Okay, so you must come up with 2 questions, one where you're going to use the one-way goodness of fit, and the other one where you're going to use the two-way independence group chi-square test. Okay, now for the former problem, you are going to include a pie chart or a bar chart. Okay, so along with the report, you will include either a pie chart or a bar chart, not both, just one. And for the latter problem, where you're going to be running the two-way independence group chi-square, you're going to report Kramer's v-square, and you're also going to be reporting the 95% confidence interval for the v-square value. Finally, you're going to write up your answers as if you were sending your results for publication. So this is your last project. You write your own questions, and then make sure you run the 2 kinds of chi-square tests that we studied in this video. And this brings us to the end of lesson 9, where we learned about the 2 types of chi-square tests that you can perform to analyze your data. This also brings us to the end of our course. It's been a pleasure working with you these last 2 months. I hope you learned a lot about Minitab, about statistics, and the different tests that you can perform so that you can publish your research academically. This is also the end of our course. Bye-bye for now. I look forward to getting your projects. Stay well.